Other trigonometric graphs. Objectives. Analyze the graphs of y equals tangent x and y equals cotangent x. Graph variations of y equals tangent x and y equals cotangent x. Analyze the graphs of y equals secant x and y equals cosecant x. Graph variations of y equals secant x and y equals cosecant x. Analyzing y equals tangent x. The tangent function is also a periodic function. Its period is just pi because its graph repeats on intervals of k pi, where k is an integer. Tangent is an odd function. We'll see this when we look at the graph. Let's complete this table of values. Here I have some angles in for x. I've shown the sine of those angles and the cosine of those angles. Now we can see that tangent of x is the sine of x over cosine x. So I'm going to take -1 and divide by 0. We know that that is undefined, so we won't have a graph where the angle is a negative pi over 2. If I take for negative pi over 3, negative square root of 3 over 2 divided by 1/2, I'll get a negative square root 3. For the angle negative pi over 4, I'm looking at negative square root of 2 over 2 divided by a positive square root of 2 over 2, and that gives me a -1. Now for the angle of negative pi over 6, the sine of x divided by cosine of x is going to be -1/2 divided by square root 3 over 2. That is going to give me a -1 over square root 3. And when I simplify that, I get a negative square root of 3 over 3. Next, for an angle of 0, 0 divided by 1 is 0. Next, for an angle of pi over 6, I have 1/2 divided by square root 3 over 2, and that's going to give me a positive square root of 3 over 3. For pi over 4, I divide the sine and cosine, I get a +1. For pi over 3, I divide the sine by the cosine and I get a positive square root 3. And then again at pi over 2, 1 divided by 0 is undefined. So we won't have a graph where the angle is at pi over 2. What happens to y equals tangent of x as x approaches negative pi over 2 from the right-hand side? The behavior is that y will approach negative infinity. And what happens to y equals tangent of x as x approaches a positive pi over 2 from the left-hand side? The behavior is that y approaches a positive infinity. So the asymptotes for the basic y equals tangent x function is x equals pi over 2 plus pi k, where k is an element of the integers. Now the graph of y equals tangent x. Let's sketch the graph of y equals tangent of x between negative pi over 2 and positive pi over 2 using values from the table that we've just completed. So I know that at a negative pi over 2 I'm undefined, but at a negative pi over 3 I have a negative square root of 3, which is about -1.7. At negative pi over 4 I'm at -1. At a negative pi over 6, I'm at negative square root of 3 over 3, so about a -0.5. and 0, I'm at 0. Then we have those values repeated, just of opposite sign, as we head towards pi over 2. Now, when I try and make my graph of this, I know I have an asymptote at negative pi over 2. I have a vertical asymptote also at positive pi over 2. So my graph is going to approach those vertical asymptotes, but it will not ever touch them. And this is our standard graph for y equals tangent x. Some observations when we look at this graph is we see that the asymptotes occur at x equals pi plus pi over 2k, where k is an element of the integers. And the x-intercepts have x values of the form pi k, where k is an element of the integers. The period is pi. We complete a full cycle of that graph in just a horizontal distance of pi. The range is negative infinity to infinity, and the graph is symmetric with respect to the origin, so this function is an odd function. Features of the graph of y equals a times tangent of b x minus c plus d. These are some standard transformations that can happen with the tangent function. The stretching or compressing factor is the absolute value of a. And remember, this a value is also responsible for the function reflecting over the horizontal axis. Okay, so it may reflect if a is a negative number. The period in general is going to be pi divided by the absolute value of b. So when you're doing this, make sure you have b factored out of all of that. The phase shift is c, the vertical shift is d. So this means our asymptotes will occur at x equals c plus pi over 2 absolute value of b plus pi over absolute value of b, k, where k is an element of the integers. And here is a nice table summarizing those transformations. Graphing variations of y equals tangent x. Let's say we want to sketch the graph of f of x equals 3 tangent of pi over 6 times x. My a is positive 3 and b is pi over 6. Remember, your period is pi over the absolute value of b, so it's pi over 6, and I can multiply by 6 over 6 to simplify that compound fraction, and that leaves me with 6 pi over pi, which is just 6. There is no phase shift here. There's no c value inside the parentheses. And there's no vertical shift. There is no number added or subtracted onto the end of this function. And let's go ahead and figure our asymptotes. Remember our asymptotes, x equals pi over 2 times the absolute value of b plus pi over b, k, where k is an element of the integers. And so if we can simplify that, we'll get here a 3 plus 6k, where k is an element of the integers. Let's say if k were 0, then this term would go away and we'd have an asymptote of 3. So let's draw in our y-axis, and apparently we have a vertical asymptote of x equals 3, And if k were -1, then -1 times 6 is -6, plus 3 is -3. And there we see our other vertical asymptote for the one period of the graph that we'll be sketching. Now I know that this graph is going to go through the point 0, 0, and I need to go ahead and decide if I have a reflection. I have an A value of +3, so that means we don't have any kind of reflection going on here. Let's make a t-table so that we can come up with another couple of points to graph. Now, if x were 2, we would have pi/6 times 2, which would make it pi/3. And the tangent of pi/3 is the square root of 3, and then we have to multiply by the 3 in front. So that's 3 square roots of 3, and we estimate on the calculator it's about 5.2. And then if I would have an x of -2, then we would have a -3 square roots of 3, because remember this is an odd function, so we get a -5.2. That takes into account the stretching of all the graph. So 1, 2, 3, 4, 5, 6. So at 2 we're at about 5.2. And 1, 2, 3, 4, 5, 6. At -2 we're at about a -5.2. And just try and make the tangent graph as smooth as you can, drawing through, getting closer to those vertical asymptotes. Alright, let's sketch the graph of y equals -2 times the tangent of x plus pi/2 minus 1. Our period, remember, is pi/b. b is just 1. So our period remains at pi. Now we do have a phase shift. Since this is a plus pi/2, we're going to be moving left pi/2. Our C value is -pi/2. The vertical shift shown here is that we will be moving downward 1 unit. And remember, our asymptotes can be found by that phase shift plus pi/2 absolute value of b plus pi/absolute value of b, k, where k is an element of the integers. So let's figure those. X is equal to our C value of -pi/2 plus pi/2 times b is just 1 plus pi over absolute value of 1 is just 1, so we're just adding pi k. This simplifies to just pi k, where k is an element of the integers. So I'll go ahead here and put in my y-axis. I know that I shifted left pi/2, so the center of my graph will be at pi/2 to the left, so -pi/2. And my period is pi, so that means that I'm going to have an asymptote here at -pi, and here's here I also have a vertical asymptote there. That goes according to the equation for the asymptotes that we figured down here. Now, do we have a reflection? Yes, we have a reflection because we have a negative in front of that. And we also have a stretch factor. We're going to stretch by a factor of 2. That means all of our vertical components will be multiplied by 2. Okay, now we need to go ahead and get a couple more points on the graph. First off, it might be nice for us to figure out where that inflection point is. I know that I have shifted left pi over 2. Okay, so once we do that, let's say if we put a negative pi over 2 in there, this would make this 0, and the tangent of 0 is 0 times negative 2 is 0 minus 1 is going to give me the coordinate of negative pi over 2, negative 1. So I go ahead and graph this point here. Normally it would be on the x-axis, but we shifted down 1 unit. Now let's go kind of midway here and midway here. So how about a negative pi over 4 and see where that lands us? If we put a negative pi over 4 here and we add pi over 2, then that's going to give us a pi over 4, a positive pi over 4, and the tangent of positive pi over 4 is 1. But remember that is being multiplied by a negative 2, and then 1 is being subtracted from it, so we end up with a negative 3 there. So at negative pi over 4, I'm at negative 3. And let's say if we are looking at this place of the graph, a negative 3 pi over 4. And I put that into my function over here. Negative 3 pi over 4 plus pi over 2 is going to be a negative pi over 4. And the tangent of negative pi over 4 is negative 1. So I have a negative 1. But remember that is being multiplied by negative 2, and then we're subtracting 1 from it. So we have here a 2 minus 1 is 1. So I'm up here at 1 when I'm at a negative 3 pi over 4. And we have enough here. We can go ahead and make a decent sketch of what our graph would look like. Remember where our graph gets pulled towards those vertical asymptotes, and so there you have one full cycle of that function graphed. Now let's take a look at the y equals cotangent x graph. I have here a table of values for cosine and sine of x for different angles. And remembering that the cotangent of x is the cosine of x divided by the sine of x, we can determine the values here. Now 1 divided by 0 is going to be undefined, which means we're not going to have a graph right there. Kind of indicative of possibly a vertical asymptote. Okay, and I have a square root 3 over 2 divided by 1/2. I get the square root of 3. Square root of 2 over 2 divided by square root of 2 over 2 gives me 1. 1/2 divided by square root of 3 over 2 gives me 1 over square root of 3. And if I rationalize that, I'll have the square root of 3 over 3. 0 divided by 1 is 0. I have a negative half divided by square root 3 over 2. That's going to give me a negative 1 over square root 3, which when simplified, we get a negative square root of 3 divided by 3. Here I have negative square root 2 over 2 divided by a positive square root of 2 over 2. That gives me a negative 1. And next, a negative square root 3 over 2 divided by a positive 1/2. That's going to give me a negative square root 3. And again, negative 1 divided by 0 is undefined, so we have another vertical asymptote there. So in the values we just calculated, what happens to y equals cotangent of x as x approaches 0 from the right-hand side? Well, y is going to approach positive infinity. And what happens to y equals cotangent of x as x approaches pi from the left-hand side? Well, y is going to approach negative infinity. So while the tangent graph is doing something like this, the cotangent graph seems to be doing something more like this. So we have asymptotes at x equals pi k, where k is an element of the integers. Now the graph of y equals cotangent x. Let's sketch the graph of y equals cotangent x between 0 and pi using values from the table that we just completed. And I'm looking at this, I have my vertical asymptote here at x equals 0. I have another vertical asymptote at x equals pi. There we go. And then when I'm looking at my table of values at pi over 2, I'm at 0. At pi over 4, I'm at 1, and I'm continuing up that way as I get closer to the vertical asymptote. And at 3 pi over 4, I'm at negative 1, and I continue to get closer to that vertical asymptote going this way. So there's just a kind of a quick sketch of your basic cotangent function. Now, just like the other graphs that we've had so far, we can have transformations of the cotangent graph, and this is the general form. Our stretching compressing factor is the absolute value of a, and remember, if a is negative, then it can also make the graph reflect over that horizontal axis. The stretching and compressing factor is absolute value of a. The period is pi over absolute value b. The phase shift is c. The vertical shift is d. And here asymptotes occur at x equals pi over absolute value b k, where k is an element of the integers. Here we are, all in a nice table. You'll notice this is the same table we've been doing for all of these transformations, which is nice. We just need to make sure that when we're doing these, that we have b factored out front of the x minus c part of our function. Graphing variations of y equals cotangent x. Let's sketch a graph of one period of this function, 2 cotangent pi over 2x minus 1 is our function f of x. And starting with our period, remember it's pi over b. b is pi over 2. So that settles out to be 2. So we have a period of 2. There is no phase shift. We do have a vertical shift downward 1 unit. And to figure our asymptotes, we have x equals pi over 2 k. And that simplifies to be x equals 2k, where k is an element of the integer. And here our a is a positive, so there is no reflection. And we can go ahead and start graphing. Start with our asymptote over here at 2. And when k is 0, then we have another asymptote here. Okay. Now let's go ahead and get a few points established here. Normally we would have a point right here and our graph would come through, something like that. But we have this vertical shift down 1. So we have a point of 1, negative 1. And you can go ahead and run that in the equation itself. Up here, pi over 2 times 1 is pi over 2, and the cotangent of pi over 2 is 0, times 2 is 0, minus 1 gives me my negative 1. Let's try somewhere here. Let's try a 3/2. If we put 3/2 in for x, we'll have a 3 pi over 4. Now the cotangent of 3 pi over 4 is negative 1. Times 2 makes a negative 2. Minus 1 makes negative 3. And let's try somewhere over here, a half. For 1/2, putting that in for x here, we get pi over 4. The cotangent of pi over 4 is 1. 2 times 1 is 2, minus 1 is 1. So we have some points to kind of give us what the shape of this curve is. 3/2, negative 3, 1/2, 1. Okay, and so I know that I'm kind of I'm doing a curve this way, heading towards, getting pulled towards that vertical asymptote. And over here the curve has changed its concavity, so it's kind of curving downward as it's decreasing. Now let's look at the secant graph. Let's analyze y equals secant of x. Completing this table of values, I have several angles lined up here, and I have the cosine values of those, because we know that secant of x is 1 over cosine of x. So we simply need to take the reciprocal of each of these values. The reciprocal of 0 is undefined, so we know that we're not going to have a graph there at negative pi over 2. Same thing at pi over 2 and for 3 pi over 2. So we're looking at some asymptotes there. And at negative pi over 4, taking the reciprocal there, I get square root of 2. The reciprocal of 1 is 1. The reciprocal of square root 2 over 2 is square root of 2. And similarly over here we have a negative square root of 2, a negative 1, and a negative square root of 2. So let's inspect to see what is actually happening here. What happens to y equals secant of x as x approaches pi over 2 from the left-hand side? So we're looking at pi over 2, and again we see this value is increasing. So y is again approaching positive infinity. What happens to y equals secant of x as x approaches that same pi over 2 but from the right hand side? So we're getting close to this angle, but from the right hand side, y will start approaching negative infinity. And the same goes for here. As I'm approaching 3 pi over 2, this value for y is approaching negative infinity. And in fact, our asymptotes are going to be x equals pi over 2 plus pi times k, where k is an element of the integers. So in looking to sketch this graph, let's first sketch the graph of the cosine function, and then we'll sketch the graph of y equals secant of x between negative pi over 2 and 3 pi over 2 using the values that we just found in the table. So my cosine graph, remember, it's going to start at 0, 1, and then the next point is at the midline. At pi, we're at negative 1. 3 pi over 2, we're at the midline. And at 2 pi, we're at our maximum again. So this is our cosine graph. And if you wanted to, we could continue this over here. Let's go ahead and do that since we're going to be graphing between negative pi over 2 and 3 pi over 2. Now I know from my table of values that we just completed, I have at negative pi over 2 a vertical asymptote. At pi over 2 I have a vertical asymptote. At 3 pi over 2 I have a vertical asymptote. And you'll notice those vertical asymptotes occur when we have a x-intercept where the value of the cosine function is 0. That makes sense if the secant function is the reciprocal of the cosine function. Now, this is actually pretty easy now. At a negative pi over 4, I've got a square root of 2, so we're about right here. At 0, I'll be at 1, so sharing a point there with the cosine graph. And at pi over 2, I'm about right here. And remember, the ends of that graph will get pulled towards the vertical asymptotes. So we've got something going on like this. Okay. And now over here, when I'm at pi, my secant value is also at negative 1. At 3 pi over 4, I'm at a negative square root 2, so about right here. And at 5 pi over 4, I'm at a negative square root 2, about here. And again, my graph is getting pulled towards those vertical asymptotes, like so. And you can see this is a graph that will repeat. We're going to have another piece that's up here. But the fact that we can graph this based off of that cosine graph makes these very easy to go ahead and graph. We could replace this y equals secant of x with y equals cosine x, graph that function. We know where our vertical asymptotes are. The vertical asymptotes are going to be where we have x-intercepts. And then we're drawing our graph off of the maximum of each of those tops there and the minimums of the bottoms right there. And it doesn't matter if we have some kind of transformation, same thing is going to happen. So just to summarize the secant graph, the asymptotes are going to occur at x equals pi over 2 plus pi k, where k is an element of the integers. Now the period is 2 pi. So the period of the secant graph is the same as the period of the cosine graph, the same as its reciprocal function. The graph is symmetric with respect to the y-axis, so the secant function is even. If our graph for secant is involving transformations, we have the same information in the table that we've had on all the other graphs with transformations. And we know that the period is going to be 2 pi over the absolute value of b. Phase shift, vertical shift, same as we've done before. The asymptotes are going to occur at that phase shift plus pi over absolute value of b plus pi over 2 times the absolute value of b times k, where k is an element of the integers. And here we have one last trigonometric function to inspect, the cosecant of x function. And we remember that the cosecant of x is the reciprocal of the sine of x function. So I have the sine values of these particular angles put in for us, and the reciprocal of 0 is going to be undefined, so we know we have undefined places 3 times in this table. The reciprocal of square root 2 over 2 is going to be the square root of 2 here and here. If it's negative, it's going to be the negative square root of 2. Negative square root of 2. Reciprocal of 1 is 1. The reciprocal of negative 1 is negative 1. So what happens here to y equals cosecant of x as x approaches 0 from the right hand side? We can see here that y is approaching positive infinity as it's approaching pi from the left hand side. Y is again approaching positive infinity. And what happens to cosecant of x as x is approaching pi from the right hand side? Y is approaching negative infinity. And when we have x approaching 2 pi from the left hand side, y is approaching negative infinity. And my asymptotes are going to be x equals pi k, where k is an element of the integers. So let's take a similar approach as we did with the secant graph. Let's first graph the sine function. Remember, the sine function starts at the origin, a quarter of the way through a period, it's at its max. Halfway through, it's back at the midline. 3/4 of the way through, it's at a minimum. And at 2 pi at the end of its period, it is back at the midline. So we have this kind of graph going on. So just the same way as we had before, whenever that function has a value of 0, then the reciprocal function is going to have vertical asymptotes. So we can draw those in, and we don't even need to be as detailed anymore. I know that I'm going to have this shared point at the max, and it goes up, getting pulled towards the asymptotes, and I have this shared point here at this minimum and getting pulled there towards the vertical asymptotes again. So observations here is that the asymptotes are going to occur at x equals pi k, where k is an element of the integers. The period is 2 pi, just the same as the period for the sine function. And the graph is symmetric with respect to the origin, so it is an odd function. In general, we have features of the graph of y equals cosecant of x with these different transformations. Again, the same table that we've used for the other trigonometric functions that have a period of 2 pi. The only difference here is that my asymptotes will occur at c plus pi over b k, where k is an element of the integers.